All right, I wanted to talk a little bit more about the IV curve now that I gave you a conceptual description of it. So I'm going to draw a graph here to that axis and rotate this. Get my y-axis drawn on here. Okay, so I'll call this axis my I current axis. I don't like that crayon. Change font type here. I'll say I milliamps or amps. I'll go with amps. Doesn't really matter actually. V volts. And I want to think about for a battery, how would the current versus the voltage look like? So what we talked about in the last video, at least what I talked about, is let's say you have a 1.5 volt battery, or actually I'll make it a 9 volt battery. Okay? When you put a small resistor on a 9 volt battery, you're going to tend to get a lot of current. You're going to have, or a small resistor on any size battery, you're going to have a lot of current. It's going to be way up here. On the other hand, when you have a big resistor in the battery, you're going to have a current that's much smaller. And then the question is, how is the voltage going to change? And what we see with batteries is that the voltage for a battery, the way you want it to be, is you want an ideal battery, a perfect battery, if there were such a thing, would have a voltage that looked like this. In other words, it would always be 9 volts, no matter what the current is. Now, in truth, the actual battery, so this I'll call as the ideal battery, the actual battery is going to stay 9 volts when the current's small, which means when you have big resistors. But as we saw in class, it's going to do something like this. The voltage is going to drop as the current increases. And when the current increases, that means you're going to have small resistor here, just a single small resistor. And it's going to get really hot because there's going to be a lot of current going through it. Battery's going to get warm, and the battery voltage is going to drop from what it's supposed to be. Okay, so this is the IV curve or IV characteristic of a battery. I want to do the same thing now, but for a solar cell. All right, a solar panel. So with a solar panel, it's a little bit different. It's going to look something like this. And this is something I normally would have my students do if we were in the lab, which we're not, so I'm just going to explain it to you. And this isn't something I was quite aware of until I studied solar panels a little bit more deeply. I didn't realize that it has a different kind of characteristic for how it delivers energy. And I was concerned. Remember, I told you never put the current measurement device across the 2 leads of a battery. So in lab, I said you never do this. Plus, minus. It's my battery. This is a big no-no. This will cause the fuse to blow, which is probably what happened before. Any of you got it, is somebody did this. This is it. You're not supposed to do that. All right. But for a solar panel, we actually can do that in many cases. It's less of a deal. And it's interesting. You can measure the current coming directly off the solar panel, unless it's a really big solar panel. But you can do it off a moderately sized solar panel. And it's kind of interesting. The current just isn't going to just go to really huge values necessarily. It's going to be limited by the physics of the solar panel. And we're going to get to that by thinking about the IV curve of the solar panel. So if any of you have a solar cell or solar panel, you could put your meter across it and measure the current, as long as it's under 250 milliamps, because that's not going to change, is what we're going to see. For a solar panel, what actually happens is they tend to deliver constant current. It's the physics of the solar panel. And it's actually something related to discovery by Albert Einstein, theoretical discovery in one of his famous papers in 1905 on something called the photoelectric effect. So this is for a solar panel. And what he found out was that theoretically, based upon what he was learning about in terms of the physics, what actually happens in the photoelectric effect is if you shine light on a piece of metal, the metal is going to release electrons. And the brighter the light, the more electrons that are going to be released by the metal. That basically means the more the current is. So under a fixed light for a solar panel, you're going to have a certain amount of current that's passing out of the solar panel. But that amount of current isn't going to change as you put resistors into the circuit. It isn't going to change for quite a while until, of course, if you just had a solar panel sitting there and didn't connect it to anything, well, in that case, there would be no current. And not connecting a solar panel or not connecting anything to something is like having a huge resistor on it. So eventually, the current's going to go down as the resistance gets big. So for a solar panel, when the resistance gets big across a solar panel, the voltage is going to get bigger. The bigger the resistance, the bigger the voltage, because remember, V is equal to R times I. Well, if I stays the same, doesn't get any bigger, but R increases, then you're going to get a bigger and bigger voltage, and that's what this part of the graph is here. Bigger and bigger voltage as you get a bigger and bigger resistor. But then at some point, your resistor gets so big that the current is going to start to drop. It just can't keep up with that. But before that, it's going to be delivering a constant current. So what's interesting about solar panels, they're going to tend to deliver a constant current, whereas batteries are going to tend to deliver a constant voltage. That's why their IV curves look different. When you hook up your 9-volt battery, you're expecting it to be 9 volts, whether you're hooking it up to something that's going to take a lot of current or not. Similarly, when you're hooking up your solar panel to something, it's going to deliver a fixed amount of current, whether the resistor is small or medium. If the resistor gets too big, then the current will start to drop as the voltage gets even bigger. All right, so that's a little bit about the IV curves of batteries and solar panels.